My name is Jeffrey Dudek, and I'm going to talk to you today about parallel weighted model counting using a tool called tensor networks and tensor contraction. And this is joint work with Moshe Vardi, and it was done at Rice University. And the general motivation for this work is that neural networks are really the golden boy of a lot of machine learning techniques, and it's a huge parallelization success story. There's been hundreds of thousands of research hours in optimizing compilers for neural network algorithms for training and inference. And this has resulted in things like high-performance libraries like NumPy and TensorFlow that perform very well in a variety of hardware scenarios, even on a single core on a CPU or even on your mobile phone, scaling all the way up to GPUs or even to specialized hardware like TPUs, Google's Tensor Processing Unit. So given this large body of work, we'd like to know if we could find some way to leverage this work for the use in weighted model counting. And what I'm going to present to you today is one such technique for doing so, which is through tensor network contraction. And the general idea began around 2010, which showed that there was an algorithm for exact unweighted model counting using tensor network contraction, which is a technique that really tensor network contraction is a technique that really originated in the physics community that has roots all the way back in the 70s. But following up from that, we showed in a paper on arXiv last year that you could pretty easily extend this algorithm into a tool for exact literal weighted model counting with tensor network contraction. And the resulting tool was competitive with a bunch of existing weighted model counters. So given that algorithm, the goal of this talk and what I'm going to present to you today is showing how this algorithm can be parallelized on multiple CPUs and on a GPU. And the key idea of all of these algorithms is that we'd like to perform model counting in some way via a sequence of matrix multiplications, with the idea being that matrix multiplications are sort of the core operation in all these neural network algorithms, which means that a significant amount of the work that goes into optimizing neural network algorithms is actually just optimizing matrix multiplication. And so we can leverage this. So before I describe to you this algorithm, let me just give you a brief background on tensors and tensor contraction, where you can just think of a tensor as some sort of multidimensional array generalizing a matrix to higher dimensions. And correspondingly, tensor contraction is a generalization of matrix multiplication to these higher dimensional objects. So I've just listed a few examples here. I'm not going to give a formal definition. But on the left is, you can see matrix multiplication, and then there's a few other expressions that you should be able to convince yourself at least look similar. We're still looking at sums of products of entries of the tensors. And the key idea here is that we'd like to identify some of the dimensions of the tensors and sum out over that shared dimensions. In the same way we identify in matrix multiplication the rows of one matrix with the columns of another matrix. And what's nice about this operation is that it's more general than matrix multiplication, but actually can be implemented in terms of a single transpose of data followed by a single matrix multiplication. And so correspondingly, all these libraries that have been produced for neural network algorithms that optimize matrix multiplication basically all have some sort of API call to perform this tensor contraction as well. So now using this tensor contraction, we can construct an algorithm for weighted model counting. And this is a sort of bottom-up algorithm. We're given a formula and a literal weight function. The first step is to construct a graphical representation of the formula. And in this case, we're using the incidence graph of the formula. And then the second phase is to find some sort of query plan that we're going to use to compute the weighted model count of the formula. And in this case, we use tree decompositions of the incidence graph as this query plan. Which is a tree associated to the graph where the nodes are labeled by some combination of variables and clauses. And there are some requirements on these labels that are based on the clause structure, and it gets somewhat technical, so I'm not going to get into it. But the sort of quality parameter that we're interested in is the maximum size of the labels. For example, if every label has size 2, then we know that the graph is acyclic. And correspondingly, the algorithms we develop, the performance will be relative to the maximum size of the labels in the tree decomposition. And moreover, there are a bunch of existing tools we can leverage to find these tree decompositions efficiently. There was a competition in 2017, a PACE competition, that produced a number of high-performance heuristic tools for generating tree decompositions. All of these tree decomposition tools are anytime algorithms, meaning you give them more and more time, and they'll gradually try and find better and better heuristic tree decompositions. And ultimately, we found in the 2019 work that it was convenient to spend about half the total runtime on planning, and the second half on what I'm about to describe, which is using the tree decomposition. And the way that we use the tree decomposition, again, is this bottom-up approach, where we start at the leaves of the tree decomposition and compute some simple information, and then pass messages from children up to their parents and all the way up to the root, correlating the information as we go. The idea of this algorithm is that we pass tensors from children to parent, pass these multidimensional arrays, and then we can express the information combination step at each tree decomposition node as a single tensor contraction of these tensors. And moreover, you can prove some properties, for example, that if you've started with a tree decomposition of width k, then you can show that all the tensors that you will be passing throughout the algorithm have as at most 4/3 k plus 1 dimensions. So you get some bound on the maximum memory you require to perform this algorithm. And I'm not going to get into it here, but there's an interesting view of this algorithm as pre-processing based on the tree width of the incidence graph, which actually generalizes some earlier work by Semmer and Zeider on SAT pre-processing to limit the number of variable appearances. And I encourage you to read the paper we put out last year if you're interested more in that relation. So this was the algorithm we presented, and there's a corresponding implementation. Before I get into the parallelization of this algorithm, I want to take a moment to step back and talk about a couple of other related algorithms, because this certainly isn't the only bottom-up approach to model counting. And basically, all of these algorithms are sort of follow from a paper from 2007 that performed model counting with tree decompositions of various graphs. And over the years, this has led to a number of follow-up papers and a number of implementations. So I described to you one from last year, which on the tree decomposition passes tensors from children to parent, and at each internal node performs a single tensor contraction. But there's some related work from 2 years ago, GPU SAT, which passes essentially an array from children to parent, and then they wrote a custom GPU kernel to perform the information combination. And there's some other differences here, but I just want to highlight this difference in the execution stage. And in follow-up work, then instead of passing a dense array, they passed a sparse representation as a binary search tree, still using a custom GPU kernel to combine information on each internal node. And then I also wanted to highlight ADDMC, which has a similar algorithm structure and got second place in the weighted model counting competition yesterday, which passes algebraic decision diagrams from child to parent, and on the internal node combination is done using ADD multiplication. Okay. So I've outlined to you this algorithm using tensors and tensor contraction to perform weighted model counting, but our original work only really evaluated this on a single core and compared it to other single core models counters. So for the remainder of this talk, I'd like to describe to you what we did to parallelize this algorithm to run on multiple CPUs and on a GPU. And the key insight here is that on large benchmarks, the runtime of the algorithm I just described is generally dominated by just a few difficult tensor contractions, surrounded by very many easy tensor contractions that appeared earlier and later in the tree. And moreover, each of these tensor contractions can be individually parallelized using existing libraries that were originally designed for neural networks. And in particular, we're going to use TensorFlow to perform these tensor contractions on the GPU. And this is the general idea. Of course, it's not quite as simple as just dropping in the library. And so there were a number of challenges we had to overcome to make this general scheme actually perform well in practice. And so now I just want to highlight to you 3 of those challenges that we faced and our solutions to these challenges. And the first challenge happens when you have high memory plans, because onboard GPU memory is very limited It varies based on the type of GPU you have, but typically it's significantly less than the amount of general purpose RAM you have available in the computer. And moving data in and out of this onboard memory is a very expensive operation relative to the rest of the computation. So what do we do if the tree decomposition we developed requires tensors that are too large to fit entirely in onboard GPU memory? And to solve this, we look back at some very classic AI work on conditioning of Bayesian networks, where the general idea is that to compute the model count of a formula, just for the sake of example, an unweighted model count, you can choose a single variable x and assign the variable to false and compute the model count, and assign the variable to true and compute the model count. This is just a very basic splitting operation. But the central insight is that if we were to run our algorithm separately for each of these two formulas, we can actually reuse exactly the same tree decomposition, exactly the same plan for both the formula when x is assigned to 0 and when x is assigned to 1. And when we do that, that means that we don't increase the size at all of the planning stage because we still use just a single tree decomposition. But we run the execution stage twice. So we essentially double the execution time of the time of the execution stage. But in return, if we choose the variable x well, so that it was involved in the largest tensor, this reduces the memory footprint that we need to run the execution stage. And what that means is that we can just greedily condition on variables until all the tensors that we plan to consider will fit in onboard GPU memory. And so this was our first solution to the challenge of high memory plans. And this, in practice, works pretty well as long as you don't need to split on more than 5 or so variables. The second challenge we had to deal with has to do with GPU overhead. And this comes from a few different places, but primarily from two. First of all, even to initialize the GPU at all, or to do anything with it, requires about 1 second for the drivers to hook up, for the memory to be initialized, all this sort of thing. And the second source of overhead is that for each operation you execute on the GPU, each tensor contraction calls requires some overhead to load the GPU kernel, which means that actually for very small tensor contractions or contractions involving small tensors, they're actually slower to perform on the GPU rather than on a CPU because of this higher overhead. And our solution to this problem was to implement a hybrid approach where we only consider using the GPU for large contractions and use the CPU for small contractions. And this flexibility was earned because we're using matrix multiplication libraries as a black box. And in particular, there's a library NumPy, which works very well on the CPU, and a library TensorFlow with a very nice implementation on the GPU. And these libraries play nicely together, and you can go back and forth very easily. So this is how we solve the second challenge of GPU overhead. And the third challenge I want to highlight has to do with the runtime of the planning stage. And I previously said that we observed about 50% of, or rather that it was useful to spend about 50% of the total time in the planning stage. But so far, I've only really talked about parallelizing the execution stage where we're doing tensor contraction. And moreover, I'm not really aware of prior work on model counting that attempts to parallelize this planning stage. And moreover, there's very limited work in general on parallel tree decomposition heuristic tools. And in order to solve this challenge or begin to solve this challenge, we took a technique that's been very highly used and very well performant in the SAT community, which is the idea of an algorithm per portfolio, where they run a bunch. In order to create a sort of master SAT solver, you can take a bunch of smaller SAT solvers, run them all in parallel, and return the first result that you get. And theoretically, this is faster than running any of the solvers individually. And so we developed, along these lines, a simple portfolio of heuristic anytime tree decomposition solvers that runs multiple tree decomposition tools, maybe with different configurations in parallel, and returns the best tree decompositions that is produced by all these tools. And I'm not going to present the experimental results here, but if you see the paper, we showed that this portfolio can actually nearly match the virtual best solver of all of these tree decomposition tools. And we see a corresponding increase in the overall performance. And this might have some applications to other tree width-based algorithms as well that use similar planning stages. All right, and so we've took the algorithm and tool we developed in 2019, And we implemented the improvements I described to produce a new parallel weighted model counter, tensor order 2, which is available online if you'd like to play with it, or attempt to use it to solve some interesting problems. And we evaluated it in comparison to existing model counters on a set of 1,900 benchmarks in the cloud using computers which had access to 8 cores and Tesla V100 GPU, which has 16 gigabytes of onboard memory. And here are the results when we're doing them. I want to highlight one aspect of this. There's the black dash line, which was our initial implementation of tensor order. And the difference between the dash black line and the black line represents the improvements from the parallelizations I've described to you in this talk, along with some other optimizations. And overall, the resulting model counter is the second best solver by par 2 score against all the things model counters we considered. There are some more in the paper. And overall, it was the fastest solver on about 200 benchmarks. So I want to wrap up. The key idea really that I've tried to get across is that tensor networks represent weighted model counting as a sequence of matrix multiplications, and so enable you to leverage all sorts of matrix multiplication high performance libraries. And we use this to parallelize weighted model counting using these high-level APIs on the multiple CPUs and on the GPU, and we parallelize the planning stage with a portfolio of tree decomposition solvers. In the future, we'd like to better leverage this parallel hardware, either by optimizing our GPU algorithms or even moving to specialized hardware, for example, TPUs, where there's more memory available than typical GPU onboard memory. Or by improving the parallel portfolio, maybe by using more advanced algorithmic portfolio techniques.